For our second and final example of context-dependent inference strategies, I want to consider how context determines our estimations of likelihood by shaping our perception of possible outcomes. And to do this, I'm going to use an example that was first published by an American mathematician and statistician from the University of California, Berkeley, named Stephen Selvin. And he published this original example in 1975. It came to be known as the Monty Hall problem, and it's nicely illustrative of the way in which content shaped these estimates. So the Monty Hall problem can be given as a sort of game. Now, we're going to play this game over and over again, and the way you win the game is to earn as much money as possible through playing the game by adopting a particular strategy for how you play the game. So here's how the game works. So before you come into the room, I've got 3 boxes. Now I'll randomly select one of these boxes. Let's say I select box number 1, and I'll put a $5 bill in that box, close it up, and you come into the room. Now you look at these 3 boxes, and then I say, pick one of these boxes. Any one of them, doesn't matter which one. So you pick a box. Let's say in this case you pick box number 3. Box number 3 is one of the empty boxes. I know that the $5 bill is in box number 1. So I will, with a perfect poker face, no tells whatsoever, select box number 2. I'll open it up. I'll show you that that box is empty, and then I'll put it aside, like so. I'll push the remaining 2 boxes forward, and then I'll ask you the following question. Would you like to stick with the box you originally chose? In this case, box number 3, or would you like to switch to box number 1? Now, suppose that you in fact chose box number 1, the box that I had originally put that $5 bill in. Then I'll randomly select between the remaining 2 empty boxes that you didn't select. So let's say I randomly select box number 2. I'll show you the contents of the box. See, it's empty, just as before. I'll put it aside. I'll push up those remaining 2 boxes, and I'll ask you that question again. Would you like to stick with the box you originally chose? In this case, box number 1, or would you like to switch? In this case, to box number 3. Now, what strategy should you adopt in this situation in order to maximize the amount of money that you win? Should you A, always switch? That is, always go from the box you chose to the other box. Or should you never switch? Always stick with the box that you originally chose. Or C, is it the case that it doesn't matter? That is, there are 2 boxes, the $5 bills in one of them, so it's a 50-50 choice. It doesn't matter which box you choose. That won't affect the outcome. So take a moment, maybe stop the video, think about it, decide what you think is the best strategy, and then start the video again for my explanation. So this problem is incredibly unintuitive to people. People will almost always say the answer is C. It doesn't matter. I can use box number 1 or box number 2 in this case. There's always 2 boxes. The $5 bill is in one of them. The odds of getting the $5 bill is always 50-50, so it doesn't matter. But in fact, the strategy that you should adopt is to always switch. Now, when you tell people that, whether they're statisticians or mathematicians or physics professors, right, they almost always are shocked and disbelieving about that. So it oftentimes helps to come up with a diagram that illustrates this point. So if we look at the distribution of possible outcomes here, we say, okay, look, I'm going to randomly select the box to put the $5 bill in. And that means over the long run, about a third of the time, it's going to be in box number 1, about a third of the time in box number 2, and about a third of the time in box number 3. So if I never switch, so sometimes I pick box 1, sometimes box 2, sometimes box 3. If I always stick with that box, then about a third of the time, I'll have a box with a $5 bill in it. If I always switch, I get the contents of the other 2 boxes. Now, the trick with the Monty Hall problem is I go through this elaborate show of revealing the contents of a box that I know to be empty to hide or mask the context of the actual choice. So I show you that empty box, and then I push the other two boxes up. And that creates this context in which you think I'm choosing between these two boxes, one of which has a $5 bill. But you're always actually choosing between the box you originally chose and the contents of the other two boxes. You'll always get the contents of the other two boxes. And so if you always switch, 2/3 of the time, on average, the other boxes are going to have the box that has the $5 bill in it. And so even though I always show you an empty box, 2/3 of the time, the remaining box that you switch to will have that $5 bill in it. So you can look at it this way, or you can think, suppose I always chose box number 1, right? And I never switch. This is always my box. Well, about 1/3 of the time, that box is going to have the $5 bill in it. However, if I always switch from box number 1 to box 2 and 3, sure, you show me an empty box, but I get the contents of the other two boxes by switching. Every time I get the contents of both these boxes. And 2/3 of the time, the contents of these boxes will include one where the $5 bill is. So again, our assignment of likelihoods, our choice of the solution to the Monty Hall problem, is strongly driven by our perception of the options in the context, even when the context itself is deceptive for us. In the next lecture module, the final lecture module, we'll wrap things up and try and put everything that we've discussed into focus.